all those that have joined us, and I'm sure there will be more joining us in a bit. Um, Myself and Jeff, we are the co-leads of the IAVCEI ECR-Net, and we also have Ethan and Catherine present from the committee as well. And essentially, the IAVCEI ECR-Net is a working group underneath the overarching IAVCEI organization. It was established during the 2013 Scientific Assembly back in 2013. And essentially, the plan is to support career development with respect to early career researchers. So, anyone within the 7 to 10 year period after their PhD has been awarded. And then to have an active network of events, support for each other, and a way to, be coordinate activities for volcanologists in the making. And so, sticking with that spirit, we have several other events that are currently in the pipeline, not just the one that you've joined today. So I'll give you a quick overview of what's coming up next. So let me see there. So up next, less than a month after this event, we have one of the master classes. And in fact, as you mentioned earlier, Jamie was actually the original brain of behind this, and now we have new members taking care of it. And the first topic for this one is forging an identity in research, and the plan is to discuss with experts how ECRs can establish themselves both as independent scientists and in the current digital age of that we're living in, and how you can develop your own research direction with more limited funding opportunities, essentially. And so this is happening on the 19th of August, 3 till 6 UTC. But if you want more information, you can register here. We have a QR code, and we'll be sending more information also via our socials. Um, Aside from that, we also have the second session of the ECR series. So today marks the first one, but we already have another one in the making. That's going to be happening on the 30th of September from 5 to 6 UTC. And we already have our speakers confirmed, who are Jordan Lubbers in USGS Alaska and Sophie Later at the Institut National de la Recherche Scientifique. And then, oops, there we go. But also, we are still looking for more speakers because we're not just using this as a platform for those that were unable to give their talks at the Scientific Assembly. But if there are other researchers that also want to share their research and they have not been able to do so at any other conference, they are more than welcome to use this platform to do so. So this is the QR code for anyone that's interested in registering as a speaker instead. But we will also be creating more information on our socials website and mailing list as more time passes by. And these are more in the pipeline. We don't have confirmed dates yet, but this is our plan. So stay tuned. We have an ECR's in action gallery, which is ongoing. And here's the QR code if you want to contribute to it. Essentially, our website has had a full do-over and it's looking pretty crisp thanks to one of our members, Eric Newland. And so one of the initiatives we have on the website is that ICRs can now submit what they do on their everyday life or in the field work or in the lab. Anything that they think is of interest, they can submit, and we will feature um, some of the best photos on the website for at least a month. We haven't decided if there's prizes yet, but maybe, if we get enough entries, that might also be something we do. And then other than that, we also have one event per month for the rest of the year. So we have an ethics in academia panel for October that is currently being organized. We will have more details later on. Same thing with a parenthood in academia panel coming up in November. And then we're hopefully going to have the third session of this ECR seminar series, thanks to Ethan, that will happen in December. And we do have also a proofreading initiative. We don't know the exact timeline, but by December 2026, we would hope that that will also be created and shared with you guys. And this is something that Jeff has been working really hard on. And it's an idea of trying to get people to people who are not first English, like first language English speakers, to have the opportunity to have someone who is a first, like an English speaker as their first language, able to proofread for them before they submit their papers to journals, just in case that can be useful to them. So that's pretty much where we're at. I will stop yapping so you guys can get onto your talks. But one last thing, if anyone is interested in learning more or reaching out with ideas or that sort of thing, these are all our socials. We have our website, Facebook group, Blue Sky, Instagram, and YouTube accounts. And this is our email. So feel free to follow and reach out should you have any questions or ideas. But enough about me. I'll stop sharing. And we'll give the floor to Ethan to introduce the speakers.
All right, thank you, Jacqueline, for the very well introduction of the whole events. So today is our first session, and very welcome from everybody. So our first speaker is Alberto Ardid from New Zealand, and he will talk about socio-economic value of data-driven eruption forecast. Okay, Alberto, the stage is yours.
Okay, cool. Thanks for the invitation. Can you all hear me? The screen is looking okay. Yeah. Sorry, I can see your faces, so I'm not getting any feedback from you. Just give me a second.
Yes, we see a screen. That'll be
Yeah.
great.
Okay, sweet. That's so good. Yeah, I was looking for my notes, but I think I just go a cappella because my notes are in here. Okay, cool. Yeah, and thanks for the invitation and the presentation. Parenthood in academia, that looks interesting. I have two little monsters preventing me to work more than I want, so probably something have to say there. Okay, guys, so today, I think it will be 20 minutes from now. Just go. I'll give you a quick talk about kind of two areas of my research. One of them is on transfer learning, on how do we use machine learning to inform forecasting places that we don't have too much data, and how do we leverage from volcanoes that actually have some data. And a second piece of work that I have been working lately that is currently accepted and should be available soon is on how do we transfer that forecasting model into socioeconomical value metrics. Everything around eruption forecasting and decision making, in particular with in data limited volcanoes. If this is the guys, so I'm Alberto Ardid. I'm a assistant professor here in the University of Canterbury. David Dempsey, he works with me here in Canterbury, and Shane Cronin, he works in the University of Auckland. This is pretty much the core of my team. Just to give you a little bit of kind of introduction to the problem, what you see on the right, this is kind of not published and not pretty much refined figure so far, but what you're seeing there is eruption frequency versus economic impact. The key idea is that kind of you have many different eruptions around the world with different scales of those eruptions, but all of them have kind of different economic impact, and all of these volcanoes have different frequency in their eruption regimes. So we know that 50 to 70 eruptions per year globally, but only a minority of them cause kind of disproportionate losses, right? A recent reminder of it are there, for example, the Whakaari 2019 eruption here in New Zealand, 22 fatalities in that case, sadly, and also on Taki in 2014 that causes 63 fatalities. Right, so that's more like a recent reminder of how the kind of damage that these eruptions could have. Something that these two eruptions share is that both of them were like short warning exposure-driven events that have disproportionately deadly. Both of them are like kind of small eruptions in a sense. Both of them are phreatic eruptions, kind of sudden small phreatic eruptions, but given the exposures of the places, they causes disproportionately losses in a sense. In this case, they were dead, causing fatalities. Another aspect for the motivation, I'll say, is that most of volcanoes also kind of lack sufficient eruption records for developing reliable local forecasting, right? So most of the eruption, some volcanoes have a quite developed like monitoring system, and we know a lot about them, but most volcanoes don't have that kind of luxury. One of the key questions that we will be addressing here is kind of what is the value of a forecasting, not in terms of its accuracy per se, but also in preventing loss of life. So we're tackling two gaps in this presentation: how to forecast an eruption in a data limited volcano, so a volcano that doesn't have like too many records of eruptive period, for example, and how do we value in terms of cost a forecast that is in essence imperfect. So as I mentioned, two gaps we'll try to fill. So those are kind of two different research, but connected to each other. The first one is the transfer learning one. We published that work in the recent years. So the key idea there is that we use seismic data, kind of historical seismic data over the last 20 years in 24 volcanoes, covering like 70 years of data and 41 eruptions. What we test there is we train machine learning models in some volcanoes and then tested in some other ones that weren't being used during the training, right? Kind of simulating this data limited scenario. You'll see here like this work coming a lot, which is out of sample skill. Out of sample mean that you test something that in data that hasn't been used during the training, right? So that's the first part of the presentation. The second part is like, how do we convert that into some socioeconomical value metric in a sense, right? The key idea of that is that we want to kind of balance manageable false alarm cost given by this forecaster that we are developing versus catastrophic miseruption, right? So that's a typical the trade-off that you have when you are trying to forecast the eruption of a volcano. On one hand, you don't want to have too many false alarms, but in the other hand, you don't want to miss any of the eruptions, right? So in that case, we will try to quantify the operational benefit of this imperfect forecast. I typically said imperfect because as we are dealing with data that have noise, this kind of system will never be perfect in a sense. They will always have like false alarms or false warnings, or you will fail, right? Just to give you an idea, also part of the context of it, this is showing the result from a study published by David Dempsey in 2020 in Nature Communication. This is kind of the research that started the whole thing in our for our work. David, what he did there was after the 2019 eruption of Fakari, he took 12 years of data of seismic data in Fakari that contains 5 eruptions, and he trained a model with the previous 4 eruptions, 2012, 2013, 2016, and another one in 2013. Train a model on those and then tested out of sample in the 2019 eruption to see if it can capture the eruption beforehand, right? And this is pretty much this is an illustration of how it works. So the model assimilates seismic data. In this case, I'm just showing the RSCM as an example. What you see on top is the model reacting to it. And in that case, what he identifies is that the model reacts to a seismic precursor 16 hours before the event, and it remains kind of in a high state before the eruption, right? The problem with this, another problem, but one of the characteristics of it is this is what we call a Taylor model. It's a model that you train using the same data of the same volcano of previous eruptions, right? But in that case, you need previous eruptions of your record for your particular in the volcano that you are studying to implement this kind of models, right? So that motivates kind of the second part of motivate the focus of my work, which is the transfer learning part. The whole idea is what I'm picturing here. You have some volcanoes that have a lot of volcanic, like Fakari, that have many eruptions recorded. We train a model there, and then we test it in volcanoes that doesn't have that luxury or that eruptive record or data scarce environments, right? To develop, when we train these kind of models with multiple volcanoes, we call them generalized forecasting models, right? It's kind of the idea. Part of a paper that we published for it, we name it like the property of its ergodicity. So ergodicity is kind of a sophisticated word. All that means is that the behavior of a volcano over time can be approximate to the behavior of multiple volcanoes. That's kind of the basic idea there. It kind of captures the idea of the analogs in volcano literature, but it's basically the same, right? The whole idea, you train on multi-volcano data set and then you test it in held out or on-sea volcanoes, right? What we identify in that study is that these generalized models kind of identify common seismic precursors before eruptions in different volcanoes, and that kind of strengthen. Then we can talk about how the whole thing works. There's of technicality, but this is kind of and also the other major result is that these cross-volcano forecasting models have similar skill to the tailored one. So we tested on Fakari too. We train a model with other volcanoes, tested on Fakari, compare the performance with the tailored one, the one trained only on Fakari eruptions, and it works. And they have similar performance, which is great. This is pretty much the key result of that, right? And we also benchmark it again, just like raw seismic amplitude signals, like RSEM, and it works better. We can talk about this figure later. I love this figure. I don't think anyone else understands it rather than me. It's very, very complicated, but I love it. If you are interested, I can show it to you. This is kind of a learning curve. This is saying basically that how many volcanoes do you need to pull in a pool to start getting like the top of the performance that you can get from these kind of models. Just to give you an example of how this works in real life, I'll say. For example, this is a series. So this is a series of machine learning models running out of sample before the 2019 eruption in Fakari. So the eruption is here. This is roughly like 2 months before that eruption. And what you are seeing here in colors are different models trained on different conditions. What I want you to point it to is that, for example, this gray line is the model trained only with Fakari data. You see in the y-axis, this is the output of our models. We call it consensus, but it's basically a number between 0 and 1 that is telling you the likelihood of an eruption in the near future in the next couple of days. That's kind of a time scale that we manage here. Basically the likelihood, so what it's saying to you is basically how similar the new data is compared to the data before the previous eruptions. That's kind of the likelihood that I'm saying. It's not a probability, it's more like a likelihood. So the green line, the gray line is the output of the Taylor model just trained on Fakari, on previous eruption of Fakari. You can see this is pretty much what you are looking for in this kind of models, something that goes like kind of low, a little bit like wobbling around in low values. But then before the eruption, in this case, like a week, start like jumping and remain at a high level before the eruption and eventually cutting the eruption in a high state. That's kind of the ideal model that you want. The blue one is a model trained not on Fakari data, but in data from Ruapehu, Ontake, Tongariros, Angelians, and Copahue, right? Different volcanoes with different kind of, most of them are more like phreatic, except for Angelians, but it's slightly similar in another way. But would you basically like try different pools and see which is the one that perform best. That's the best way to train these kind of models based on and select the best one, right? And you can see here it also performs quite well. It's also giving you these high points here, which could be false positives, Depends on, but it could also be reflective of pre-eruptive activity. We can talk a little bit more about the false positive side and the physical interpretations of them. But this is another example for Besimiani in 2019. Similar stuff. You have different models trained on different conditions without seeing this eruption in particular. One of them trained on also in phreatic eruptions. So curiously, is the one that performs best. Seems to be like, as you can see here, the blue line goes really low, and then before the eruption, it goes high and cut the eruption in a high state, right? So this is pretty much when I say out of sample, is imitating the real condition as far as we can. We call it like pseudo prospective, right? Because we haven't seen the data to the model, and then we run the model kind of as supposedly real conditions, but this is, the closer that we can get to real. Okay, so one thing when you are testing these kind of models, one thing that is important is to check how they perform before the eruptions, right? If they actually caught the eruption in a high state. But the second key question is how these kind of models perform for over extensive periods of time, right? Can it discriminate between eruptive and non-eruptive data, for example, right? What you're seeing here is also 3 models running over 10 years of Fakari. In Fakari data, you can see in red the eruptions. So one is here, another one here, 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 and here. Those are 5 eruptions. And you can see the models kind of wiggle around, and sometimes this is the 2019 one, great performance before, but also you can see some false positives over the whole thing. So the key question here is how do we turn a continuous forecast into something that we can score, right? The way that we do it is applying a decision threshold in this case, right? For example, we can say, let's put a threshold of 0.765, and then based on that threshold, let's count true positives, true negative, false positives, and false negative, right? A true positives, you caught an eruption, the model caught an eruption. A true negative, a non-eruptive data well classified as non-eruptive. False positive, and false positives and false negative, right? Kind of the same narrative around. You count all of them, and then you evaluate the performance of the model. However, I guess you're all already asking this. There are 2 things here. What is the criteria for defining what is a true positive, a true negative, a false positives, and a false negative? And how do you set the threshold, right? In this case, it's kind of arbitrary, the decision that I made of 0.5, but that's kind of biased in a sense, right? So the first one, how do we evaluate the performance? This is an example of how do we count the true positives, false positive, false negative, and true negatives. Basically, if you have okay, welcome you there. This is an eruption. This is the performance of the model. For example, we say 2 days before the eruption, everything that is higher than the threshold, we consider it a screen, which is a true positive. Everything that is lower is considered a false negative, right? A data that is classified as non-eruptive, but eventually lead to an eruption. And we set this pre-eruptive window of 2 days. There is a reason for it we can talk about later, but the rest of the signal we classify it as false positive when the model is trespassing the threshold, right? And well-classified non-eruptive data is classified as true negative, right? So this is pretty much the criteria that we use for defining those for extensive periods of time, right? The other key question is how do we decide what the best threshold is, right? For that, we use something called an ROC curve, which is doesn't matter what it is, but the name of it, but it plots the false positive rate versus the true positive rate for different thresholds, right? So this little animation, what it's saying is that basically you pick a threshold, right? For example, I pick a really low one here, and then I count the true positives, false positives, and so on. If I pick a really low one, I get a false positive rate quite high. Everything will be classified as a false positive, and everything also will be classified as true positive because I'll be cutting all of the eruption, right? So in that case, the point is here. So each point in this curve is one threshold where you quantify for that threshold the false positive rate versus the true positive rate. The way to read it is that basically everything we want to get here, right? So we want to have minimum false positives and maximum true positives. So everything you're hoping to get here, right? So the closer from this diagonal to this corner, the better the model, right? So, and you can count it for multiple thresholds, right? So this is an unbiased way to quantify the performance of your model, regardless of the threshold that you're using, right? What else? You can also get this number, AUC, which is the area under the curve. That tells you it's kind of a single number that quantifies the performance of the model over any threshold possible over extensive periods of time. One cool thing about these ROC curves is that it works for any time series. You can put here the output of different machine learning models. You can put the RSEM. You can put the Shannon entropy. You can put the whatever time series that you are using for evaluating or use it as a forecasting the eruptive activity. You can plot it here, and then you can plot the results here and compare the different models using the AUC. So pretty cool stuff. We did that in that study, compared our machine learning models with the RSEM, purely RSEM. Overall, what we got is that our models, based on this metric, it works quite kind of outperform the typical metric. So it works better than just using the RSEM for pre-eruptive purposes, at least. One thing that we can talk about this figure later. This is just comparing the RSEM with our machine learning model against the VEL, the volcanic alert level for Fakari. But basically, what I want you to point to is to this block. So this is pretty much a summary of the performance of our best model on Fakari. So Fakari have over the period that we work with, which is 10 years, it contains 5 eruptions. Our best model caught like or anticipate 4 out of 5 of those eruptions. So this is pretty much like 80% of accuracy, but I think it makes more sense just thinking about 4 out of 5. Then we can talk about the one that we missed there and what are the reasons for it, but that's kind of the objective metric that we got. And on the other hand, at a cost of 10 days of false alarm per year, right? So this is pretty much the best performance metric that we have, 4 out of 5 eruptions at a cost of 10 days of false alarm per year, right? So that's the case for Fakari. Okay, guys, so let me take you to the other part, which is it will be hopefully a little bit quicker. Potential economic value. So the key idea is that let's think about not only about performance, but let's think about to quantify the performance of these models in terms of cost, in terms of money, right? So this is something that we adapted from meteorology, from really old papers. Basically, the key idea is to compare 3 strategies. What happens if you act on an imperfect forecast, like the RCM or our model or some other one, compared to never acting to a forecast? And if you have a perfect forecast, an ideal forecast, we can compare the cost of the 3 of them, right? So the key idea is like, this is the picture that I showed you before. First, we just count for the result of a forecast, the false positives, the true negatives, and so on. And then if we assign or we assume a cost for a false positive, right, or a false warning, how much does it cost a false warning compared to a missed eruption, right? And we can put it in this little formula, the cost of no forecast minus the cost of a forecast divided by, it's basically a ratio comparing the cost of acting to a forecast compared to a perfect forecast, making some cost assumption to the false positives and the false negative, right? So that's kind of the key idea. The key point is like, regardless of the cost assumption that you make, there is kind of the key idea is there is a asymmetry between, the recurrent but manageable cost of false alarms in terms of closure of the volcano, evacuation, depends, is case by case. It's different if you have a volcano in the middle of for example, in New Zealand, Ruapehu is in the middle of the North Island, highly populated area. Whakaari is a touristic island, of course, and that is different. The cost assumption for a miseruption or a false alarm is different compared to a remote volcano in Alaska that is monitored for air purposes, air traffic purposes, for example, right? So it's pretty much case by case, but the key, but the asymmetry between those is what remains between them. So just to give you an idea of how this result works, basically, when you make some assumptions, of course, for example, for Whakaari, we assume like the cost of a false alarm is around $500,000 in terms of tourism blockage and stuff like that. We can talk about also the assumptions later, but we test a range of assumptions, and the cost for a miseruption is around $10 to $20 million based on cost of life and some other stuff. But this is the way that we look at the results. So for a certain threshold in our model, so you have the result of your model over extensive periods of time. You select a threshold. For that threshold, you count the false positives and the true positives. And then if you assume some cost for them, you can count what is the potential economic value of this particular forecast. So what I'm showing here is, for example, a lower threshold mean is a risk adverse, right? So you evacuate the volcano or the region around the volcano often, and it costs a lot, right? Because you are evacuating too many people too much time. On the other hand, if you are a kind of a risk-taking, if you take a risk-taking approach, you evacuate rarely with a high cost when a missed eruption happens, right? When you miss an eruption. Then if you make some assumptions about those costs, you can transform that in what is net saving of using this kind of forecasters compared to not using anything at all, right? Another cool thing, you can compare different models and see which is the one that kind of perform best. Sorry, something happened there. So the result always look like this humped shape potential economic value curve. Low threshold, too many false alarm, high threshold, missed eruption, right? So it's always a trade-off between those two. In this case, we identify this is for Whakaari, we identify a threshold of 0.8 that save basically a bunch of money over 10 years of our simulation in a sense, right? Of course, we did a lot kind of a Monte Carlo sampling over the cost assumption, and always the value seems to be positive, given the high cost of missed eruptions, basically. This is another way of looking at the result, which is kind of the cumulative cost over the time. For example, this is for Whakaari from 2010 to 2020. The green line, what you are seeing in the green line is if you react to the result of our machine learning models. So you typically have a small cost from frequent false alarms for access restriction, basically. But on the other hand, what you have is in the red line, if you don't have like any forecast at all, seems to be flat all the time, but every time there is an eruption, the cost jumps quite massively. So that's kind of the basic idea, right?
Sorry, Alberto, you
yeah.
have about like 2 minutes to wrap up.
Okay, cool. Just
thank you.
I'm finishing already.
Okay.
So the key thing I think about this is, accepting a high false alarm rate is economically rational over the long horizon, right? This is just some kind of Monte Carlo testing about the cost assumption based on if you are more risk-seeking or balanced or risk-averse and so on. Practical lesson from there, if you are a very cautious-looking high threshold, can actually be dangerous, can be a dangerous choice, and that is the case for the VEL. So key insights on one hand, we have these kind of models that can be trained on data-rich volcanoes and implementing on data-scarce volcanoes with similar accuracy. And on the other hand, we try to quantify the value of this forecaster, not using only the accuracy, but also the cost assumption, the cost of reacting to this kind of model and not reacting to them. So, okay, guys, that's it for me. Thank you very much. I think I took a little bit too much, but thanks for your attention.
All right. Thank you, Alberto. And anybody have any question? And we can take maybe like 2 questions. If you have a question, you can just turn on your speaker or you can text in the chat.
I would ask a question or two. I had a question sort of about each part, if that's all right.
Yeah, that's all right.
So the first thing I wanted to ask was maybe more of a curiosity, and it's not exactly the point of the presentation, but I was curious about in the first part where part of the process was comparing the Facari model with the model drawn from different sets of volcanoes. And I guess you were saying part of it was try, I guess, I don't know if you were trying different groups of volcanoes to see how they compare. And so I thought it was interesting when you had the two you were highlighting the
tailored
pool
one and the phreatic pool.
Yeah. And so I wonder where they were quite well following each other at points, but then there's points where they were following each other quite well, but then they move apart. I wonder, just more from a curiosity perspective, from spending all the time with the data, were you able to sort of identify that certain volcano was responsible and then take it from the pool, or if that sort of meant something to you?
Yeah. So we have a sense of which are the kind of the volcanoes that seems to have that are more informative, for example, for Facari, right? So in that case, the Copahue volcano in Chile seems to be the one that is contributing with more precursory activities similar to Facari. However, those models, when they differ, is basically one of the model, the tailored one, just have seen the eruptions from Facari. So it's kind of, is reacting only to what have seen in Facari, while when you mix a bunch of other volcanoes, it's also reacting to some pre-eruptive activity in some other volcanoes, right? So, which don't necessarily mean that that type of activity, that pre-eruptive activity on other volcanoes, is also a pre-eruptive activity in Facari, right? The key idea for these models is we test we compute many features, over like 400 features. And then for each volcano, we have a filtering where you select the ones that are more relevant for that one in particular, right? So yeah, there is a lot of work to do on try to understand the different precursors identified for different volcanoes and what they mean. Not all of them are necessarily physically interpretable. Some of them are. But at the end, I think the key question is that do we want to be interpretable, or do we want for them to be, actually anticipate the activity? Well, of course, we want them both to be those two characteristics, but yeah. I hope that answers some of the,
Yeah, no, thanks. And then the other thing is just quick with regard to the last part with looking at the risks of false positives and the risks or the cost that you mentioned of 10 days of volcano
false
closure,
alarms,
sort of in the false alarms. I wonder if in presenting this work to, I guess is it Earth Science New Zealand now, or to government agencies, if you've had any feedback on sort of, you have your model of that you've calculated, what is a good result, and I wonder if they have feedback as far as what do they consider acceptable as far as false positives, or if you've had any interaction with that.
Yeah, of course. Yeah, I work kind of closely with some of the people here from ECR-Net, which is the group inside of Earth Science New Zealand that monitor. Yeah, there you have like Oliver Lamb, I think he's asking. Oliver Lamb, I have worked with him and some other guys, and All of them are quite positive, I think, about what we are doing, and we are designing a path to kind of implementing. We have some level of implementation, but so far we want to test these models like over like an extensive period of time before I start making decisions around them, right? Because it costs, and of course, like we can say a lot, but then when they make a decision, they need to also pay the price if those decisions are wrong. So yeah, like moving from like pretty method to decision making is also a big thing. Yeah.
Thanks a lot, Alberto.
Good. Thanks, man.
Okay,
Darren, you have a question? Yeah.
Yes. No, Alberto, nice talk.
Super.
Just really
Thanks.
quickly, maybe not really a question, but a blend of a question and a thought. But you showed this ROC curve, and
Yeah.
that's great. I love it when machine learning like applications show that. But I kind of want to think in the context of like forecasting an eruption and like getting a false positive. I kind of want to say like the cost of a false positive, it feels kind of high in volcanology, not just from an economic standpoint, but also in the context of the public's faith and confidence in the observatory. So I kind of, looking at the ROC curve, I wonder if we would want to lean, not right at the corner of the curve, but actually towards a lower false positive rate. And I'm curious if you've thought along that line before.
Yeah. I remember writing when I was trying to implement this potential economic value. There is a lot of literature in other fields that this kind of cry wolf effect, that's kind of the way that they call like, eroding trust in the models, giving too many false positives. There are some other fields that seems to be more comfortable with, like, I'm thinking tornado, tsunami, there is a lot of research on it. But as you said, like, seems like in volcanology, the acceptance of false positives is quite different from them. People, yeah. So I think the key message there is that as a community, we need to transmit that having false positive is something that we need to accept in order to be able to forecast, to anticipate the eruption properly, right? Because there is a big trade-off into any model anticipating an eruption compared to the false positives that you get, right? If you want to be accurate on anticipating the eruption, that comes with a cost in terms of a false positive, right? So there is a big discussion around that, like how to communicate that, but yeah, I'm not a social scientist on that side, but I think those are the kind of key questions that we need to also address as a
Thanks.
Yeah.
All right. Thank you, Alberto. Really nice talk and really good answering. So we are a little bit slower, but then if you have more questions, feel free to email to the speaker, or if Alberto, if you stay around, you can continue to answer some question in the chat. And so our next speaker is Darren Tan, and he will share about his idea about what he learned from machine learning for volcano seismology. And I will raise my hand if there are 3 minutes left, so you sort of know how much time still left. Okay. Yeah.
All right. Okay. I hope I've unmuted myself. Anyway, thank you for the introduction, and I'll try not to yap too much and stay within time. So yeah, so thanks again for the invitation and for coming together for me to present. Today I just hope to share with everybody kind of like more of a personal experience of developing a machine learning model tool for volcano seismology. Actually, for me, I've dipped my toes into machine learning during my PhD, but my recent research actually.
Sorry to stop you whilst you're
Yeah.
talking, but I think better to nip it in the bud now. Your slides, for some reason, they didn't go full screen, so now we're seeing only part of the screen.
Thank you. Let me try again. Sorry about that.
No, take your time.
Okay, what about now? Is it better?
No, it's still not
No, I
going
think
full
it's
screen for
just-
some reason.
Not full
Yeah.
screen.
So we see
No,
It's,
it's-
it's staying like a quarter of the screen. Like the screen kind of tries to go full, but 3/4 of it is black, and the
You
rest
see the
is
whole
just
slide.
slide.
Mhm.
Okay, should I just do it this way then? Is this
Yeah,
better?
maybe this
You're
is better. Yeah.
comfortable. Yeah,
Yeah.
that's
Okay,
actually is larger, so go ahead like that. Yep.
Okay, sorry about it. But yeah, I'll
you're
just
good.
proceed from here.
Yeah, go for it.
So again, today I wanted to share kind of like a personal perspective of what I've learned through building a machine learning model for volcano seismology. Actually, for me, I kind of dipped my toes into machine learning during my PhD, and my most recent research, I've kind of stepped out of it. But through this process, I feel like I've learned a lot in terms of designing a machine learning model and, putting it out from an operational standpoint while I was in Alaska. So yeah, just a quick overview of how I got into machine learning. So actually right now I'm presenting from Singapore, which is where I did my undergrad. But between the years of 2020 and 2025, I did my PhD at UAF and worked closely with the Alaska Volcano Observatory. And most recently, I was hired back by Singapore, but I'm currently a visiting postdoc in Tokyo. So point is, I did my toes into machine learning and I've kind of applied it on volcanoes that these respective universities have an interest in. And yeah, going back to my PhD between 2020 and 2025, that was pretty much right around when machine learning started to take off. So this is a very nice review paper from 2019 that talks about how machine learning is going to lead towards data-driven discovery in solid Earth geosciences. And I think soon after this publication in 2019, we really started to see an inflection point of ML publications in volcanology right around 2021 and 2022, I want to say. So given this context, I wanted to kind of focus in on this title, but also zoom into the context of volcano seismology, which is my expertise, and also zoom into the lens of myself as an early career scientist. So going very specific and personal here. So, okay, I'm going to zoom out a little bit so I can see the whole slide. So my primary contribution to machine learning in volcano seismology is this model called VoiceNet. In short, it's the Volcano Infrasound and Seismic Spectrogram Neural Network, which is a mouthful. This was published in 2024 because I was assigned basically Pavlov volcano in Alaska for my research. And this, like Alberto said, I developed a tailored model, which happened to work very well on Pavlov volcano signals. And following that, my collaborator in AVO, John Lyons, was like, hey, your model looks kind of good. Could I train it for my volcano? And that's what he did. And we added 2 volcanoes worth of training data sets. And then that led to this paper on the right. And then my PhD advisor was like, hey, if it works on 2 volcanoes, why not more? And, given his research connections, he was like, okay, let's pull together as many volcanoes as we can. And we try to build a generalized model. And this again led to a paper and a presentation at IAVCEI last year as well. So, okay, that's a lot on what this model has done, but how does it work and why did we exactly pursue machine learning as a whole? So I think VoiceNet was primarily motivated by the need to monitor volcanic tremor, which for the uninitiated is this very temporally variable and semi-continuous seismic signal that we often see close to volcanic eruptions. It's very challenging to detect and classify tremor because it has variable amplitudes and spectral features from volcano to volcano. And it also ranges wildly in terms of durations. We could see it in tens of minutes, hours, or even days to months. At volcano observatories, and I'll say this for the Alaska Volcano Observatory, tremor is often monitored through spectrogram images. So here at the bottom, I have kind of like the seismic waveform and also the spectrogram equivalents of the same time period. And on the waveforms, you see this continuous wiggle, but you aren't quite sure whether that's wind noise or because unlike an earthquake, it's not like an impulsive onset. But in contrast, in spectrogram images, you kind of see this high-powered signal manifest as swaths of red shown here on the spectrogram. So if you think about that monitoring task of yourself looking at a spectrogram, it kind of presents itself as a machine learning opportunity because you think about computer vision and classifying cats versus dogs. Here we're classifying signal versus non-signal. So again, at the Alaska Volcano Observatory, we cover quite a lot of volcanoes. And when I was a student there, I also served as a duty seismologist. And when I'm a duty seismologist, every day we scan 24 hours of spectrograms. And here are just 2 volcanoes, 5 stations, and we have like 30 plus volcanoes to go through every day. And here on these spectrograms, you can see this like lighter colored swaths, and these are all real tremor, both of which happened in 2021. It's kind of hard to assign a start time and end time because sometimes it's pulsating, as shown in the second row here. And right now, the extent of monitoring these tremors from a duty standpoint is just saying, yeah, I think I saw a tremor on this volcano on this date. Let me just pen that down in a sentence. So no start times and end times, no characterization of the spectral features per se, at least not systematically or formally. So again, imagine your eyeballs going left to right, every row, every column, every volcano. And, it's a pretty laborious task, right? So that led me and my advisor to the motivation of designing VoiceNet. So I've given a talk on VoiceNet a couple times now about, like how the architecture and like where it's done well. But today I just wanted to use the time to talk through how we designed it and, what are some decisions we made along the way, which I feel like are important, but don't quite make it into the papers necessarily. So initially we knew that we wanted to emulate, the detection of tremor. And, back in 2022 or 2023, there's like, there's all like supervised, unsupervised, and it's like a whole plethora of stuff that we could choose from, right? And I think to summarize, we had some guiding questions. So think of this slide as like a flow chart. So firstly, do we want to go supervised or unsupervised? And for those that are not familiar, supervised models are the ones that require labeling, but the output is then taken from a set of predefined classes, right? Like the model cannot come up with something new, but as long as we have an expert defined set of comprehensive classes, it's basically forced to choose from those. In contrast, unsupervised models, you kind of just give it the whole data and it just finds a pattern to the madness. And it tries to partition a predefined duration of activity. And, it gives you like 4 or 5 clusters, I guess n clusters, and you have to define n. But the interpretation of the cluster comes after, which I think is a very key aspect. So on that question, we decided to go with supervised because from an observatory standpoint, we wanted a deterministic output. We did not want a model that finds a pattern, gives us some clusters, and then the interpretation comes afterward. We wanted the model to do exactly what we want, and given that it would do exactly what we want, we hope for greater longevity in the model, and also the hopes of transferring this expert intuition from volcano to volcano. So after deciding that we wanted a supervised model, we had to choose what classes we want. And at that point, we started coming up with a laundry list of classes. Like, yeah, it's machine learning is a new in thing. Let's just throw everything in a bucket, right? So we just think from a volcano seismology standpoint, yeah, let's have earthquakes, let's have tremor. How about explosions? Oh yeah, don't forget paroxysms, lahars, rockfalls. The list goes on and on and on. And at some point, we had to weed that down to the core classes that we actually want. So the first consideration is, yes, VoiceNet is tuned for tremor. So let's just throw in a couple different classes of tremor that we think are comprehensive. And at that time, we also wanted to keep classes signal-based rather than process-based. And what I mean by that is that seismologists, interpret a signal as a rockfall or a lahar, and and that at its core is an interpretation, right? That maybe is validated through a webcam image or validated through an infrasound signal per se. And we didn't want our model to overreach, and we kind of wanted to be like a stepping stone from actually analyst-based monitoring, just one step up from that towards a machine learning guided intuition. So we wanted to keep it signal-based. So another thing we wanted the model to do is to detect events, and that led us to adding the noise class, where if you imagine, again, the eyeballs moving from left to right, if we go from noise, signal, that primarily serves as a detection mechanism. Even though I think there are some machine learning experts that argue against this because noise really has no no systematic trend in the signal compared to some other volcano-related signal, and it might therefore lead to some confusion or some mistraining of the model. But in our case, it seemed to work, so we're quite happy with that. Oh, sorry, scroll down. So after which, we trained the first model on this set of classes, and then at my volcano, I started getting explosions. They were getting confused with earthquakes. So despite our guiding principle of signal-based rather than process-based, we decided to let in explosions, which have kind of like a characteristic seismic manifestation. And after which, we started finding that long period earthquakes share some characteristics of explosions, and it led to a lot of misclassifications of LPs as explosions. So that led us to separating the earthquake class to VTs and LPs. So overall answer to this question is that, yeah, we start with a laundry list. We think in terms of guiding principles, but in the end, there's some trial and error and some compromise involved. And this was the final set of classes that we decided upon. And the last question was, do we want to do shallow learning or deep learning? And again, just a brief overview, shallow learning involves the extraction of expert-defined classes, whereas deep learning, you're giving it the full signal and it just like finds some patterns within the continuous waveform or spectrogram. And usually for interpretability, most people would often opt for the shallow learning approach, where you have a clear expert-defined feature that has physical meaning. But in this case, we actually opted for deep learning, mostly going back to this to emulate the eyeballs going from left to right, which is essentially computer vision, but in our brain. Or rather, the computer vision is like the same process, but in terms of machine learning, to flip that around. So again, to hammer down this intuition, instead of classifying dogs and cats, we're just classifying what is a signal across the different types to noise or data gaps and whatnot. So leading on to that, we develop a model. Again, there's a paper on this. And the generalized VoiceNet with the 8 volcano dataset achieved an overall accuracy of 87%. It's a convolutional neural network that takes in a spectrogram slice and then basically classifies it to these classes on the left over here. So moving ahead here, this is our timeline plot that I've shown many times across the different presentations. And this basically demonstrates how VoiceNet classifies a regular time sequence. Here it's 3 hours of seismic data from Pavlov volcano. So first, because our model takes in little 2-minute swaths, we slice that up, we classify them individually by station, and this gives us the colors at the top, which are indicated by the class color bar on the right. Most of the times it agrees. So as you can see, all across all the stations, we kind of get this consistent blue swath, but this is not always the case. So in the later part, there's some confusion. So what we do is that we do this compilation vote, adding the probabilities and choosing the best class across the whole network of stations. And correspondingly, summing their probabilities, we also get this normalized probability through our network. So again, showing these probabilities and also calculating amplitude to visualize alongside that. So overall, something like VoiceNet could take the input spectrogram and summarize that in the colored swath that it tells us it goes from monochromatic tremor to this dark colored gray quiescence period to some long periods and explosions, and then finally broadband tremor. So at this time scale, we designed this plot really to facilitate a one-to-one comparison of what's the data, what's the analyst interpretation in our heads, and what's the model's interpretation at the top. And I think that's important because that builds confidence, which I'll get to later. So again, that plot that I showed in the last slide is really just 3 hours of data, which is, given machine learning, is just 12 seconds of processing time. And that gives us the power to scale up the analysis very, very quickly. And so for me, who worked on Pavlov, the 2021 eruption was notoriously long. It lasted almost 2 years. And I could come up with a figure like that in less than a day, which is pretty awesome. So here, just to distill that figure again, the top row is the AVO's aviation color code, which is a proxy from unrest. And then the bottom here, so as to not squish the colors all too much, we decided to show it in a different way, where these little columns show class prominence, and the opacity of each pixel is mapped to the number of network vote counts per day. So bringing back to classes, interpreting this timeline, we see the reds, the greens, and the blues intermixed in the pre-eruptive phase, showing tremor diversity. And then we could see in the main eruptive phase, we see this transition from blues to red, which is a shift from monochromatic to broadband tremor. And at this point, we can also piece out different things like explosion-rich periods, and we could scale that up to multiple eruptions and then make cross eruption comparisons. But the point of today's talk is to not talk about the scientific conclusions of that work, but rather the design choices, right? So stepping out a little bit, we make these cross eruption comparisons through VoiceNet timelines, and we discuss our findings there. But I think what's more important through this exercise is that the analysis and acceptance of this analysis through machine learning was kind of made possible by building confidence at multiple levels. First, in the familiarity of the classification process, our eyes are scanning left to right, and so is the machine learning model. And also this idea of verifiability in shorter discernible timescales. So for instance, would you be able to believe this if not through building confidence at this level first? So kind of like a stepwise approach towards believable and appreciable machine learning outputs. Okay, so my last few minutes, I wanted to talk about what has happened post-publication. So VoiceNet has continued to show some operational and research use, primarily in Alaska. So here is a post from just a couple of weeks ago, someone saying that, hey, I'm still using VoiceNet, and they're using it to detect some LPs at Alaska, which is, for me, great to see, even after I leave. My advisor has continued to use this to look at some more recent eruptions as well, which is awesome. And funnily enough, for me, I went to work in volcanoes in Japan and Indonesia, and this model completely broke because there was a site-specific noise. I could go on and on about, the issues here. And, essentially, it boils down to the type of seismic signals that we see at some other volcanoes do not match our 8 volcano data set. And so even with 8 contributing volcanoes, the model was unable to generalize to these unfamiliar settings and unseen signal diversity. Yeah, Ethan, I see you.
Yeah. Okay.
Gotcha. Yeah. So, this is the part of the talk where I say ML is just getting started. And I show like the exponential curve in AGU abstracts with machine learning in their in their descriptions, right? But since today is I want to give a personal perspective. I wanted to share this little provocative bit. So an unforeseen consequence of my work on VoiceNet is that now I exist in this relatively small pool of volcanologists that have used machine learning. And after publishing VoiceNet, I've gotten quite a bit of like review requests, and I hope there are no editors in the audience right now, but yeah, in 2026, I've gotten a lot of review requests, and like here are just the ones that I've accepted, and I feel like there's a growing number of machine learning publications in the literature that are waiting review and wanting to be published and whatnot. But the point of this plot is that having seen quite a few recent machine learning works, is that I think as I start opening up these papers, and this number of papers are ballooning, I think I immediately jump to this kind of like a preset notion of what are some clear markers of a sound machine learning contribution in volcano seismology, and what's leading to myself to maybe like have some type of concern for these papers, or like me wanting to reject them. And Alberto talked about ROC curves, and whatever's in the first point is really just sound machine learning practice, right? But I think at the end of the day, as a volcanologist, we want the model to achieve clear monitoring and scientific goals, rather than just an endless pursuit of accuracy. And I guess as an example of that, if we have a paper classifying VTs and LPs, and they're discussing just strictly accuracy, but what I want to know is, where did your events come from? Were they before, during, or between an eruption? And assuming if your classification accuracy is perfect, how exactly will it benefit monitoring procedures? So going back to just questions in grounded in volcanology as a science. And I have a couple more slides here that is essentially just a review of like machine learning works in the field. I just skip over that for the interest of time. But I think right now the field has a whole range of machine learning applications. We have PNS phase picking at volcanoes, event classifications like I did, regime classifications for long erupting volcanoes. And we have eruption forecasts like what Alberto shared earlier. And I think these methods kind of fall in an axis of, operational optimization versus, giving the model more responsibility of inferring making inferences about the volcanic system. And on that end, I feel like there's more scientific discovery when we leave more to the machine learning model. Just one more provocative bit, if I may. So this is my take, putting my hand on the pulse of machine learning and volcano seismology. How much would I be willing to trust a machine learning model to make decisions for me over that of a human? And I feel like for PNS face picking, I think we're starting to see quite a lot of evidence that is doing it more systematically and reliably than humans are. And so a pessimist me would say that, yeah, maybe the bar is right here right now. But, from the benefits of VoiceNet and, some other works in the literature, I feel like, we're approaching, the right side of the axis quite rapidly. So an optimistic take will put us around here. And then, of course, by relegating these tasks to machine learning models, we start to ask the question, for eruption forecast, can we truly go fully on that end? And yeah, I guess that remains to be tested and seen. So I guess I'll just end off here for the interest of time. But, given this axis, I just want to hammer home that, amidst all this wild west of machine learning stuff that we're seeing going on, just doubling down on monitoring needs at observatories, the accuracy and timeliness of forecasts and our understanding of volcanic systems. That's at our core what volcanologists hope to do. And I think machine learning is simply just a means of getting there. And let's not lose focus. Okay, I'll end here. Sorry for going over time.
All right, almost perfect. So thank you, Darren. Are there any questions you want to ask? Okay. I have a question myself. So I'm not a modeler. I'm also not doing this volcanology, volcano monitoring data. But to me, I think you touched a little bit on that some of the data is kind of sharing similar feature as earthquakes. So I was wondering, is it like, to you, this seismology data is more like a Saturday anomaly? Like in earthquake, you have anomaly that it tells you there is earthquake happen, and then in volcano eruption, you also have sort of anomaly and tells you there's volcano eruption. Does it mean you are able kind of provide a generalized model to cover these two? Or for different scenarios, there are specific features you have to look at specifically to tell that it's volcanic eruption?
I think this goes back to our decision to take a signal-based approach rather than a process-based approach. Because from my experience with Pavlov volcano specifically, we would see just a continuous single class classification of broadband tremor throughout months and months. But at the volcano, through webcams, we actually see, and satellite images, we see changes in eruptive activity. And that speaks to me as seismic data not being able to do it all. So I feel like, yes, the continuous seismic data stores a lot of interesting things that is worth picking out. But at the end of the day, I think volcanology is still a multidisciplinary exercise. We can do our best detecting anomalies and classifying events from a seismology standpoint, but it really takes a whole village to make a comprehensive and sound forecast and evaluation of volcanic activity.
Okay, thank you. Yeah, there's one
Hi,
question.
Darren.
Hello.
Yes, very, very nice talk. I have a question also. So with your axis here with pessimistic 2026 take on the left and then going more towards forecasting, I was wondering, since in my mind, if you build machine learning models to do the tasks that are more on the left of the axis, you're kind of setting stones to build more towards the right of the axis, or in my mind, you need more fundamental advances on the left to be able to even reach towards the right. So I was wondering, after building VoiceNet, have you seen in Alaska that they're building on this to try move more towards the right of the axis, like automating anything further than tremor classification, or not?
Yeah, no, good question. I think, okay, I'll answer it in two parts. I think from Alberto's talk earlier, I do feel it falls perhaps on this side of the axis, and what I'm doing here is on this side of the axis. When you mention stepping stones, I think those are important, but it also does not have to be, one directional from left to right, right? I think what Alberto has presented and done is obviously important. So it's something, in my mind, I envision it meeting in the center, right? We need people to do research on both ends and start eventually bridging the gap by taking into account, what are the monitoring needs and, any newfound new findings about the volcanoes that you're doing your research on. Specific to AVO, I know that after VoiceNet, there was definitely I wouldn't say a surge, but definitely increased interest in like using machine learning to automate things. Specifically at AVO, we have a very well-known P and S phase picker, and he's retiring soon. So I don't think we're able to find somebody with his same level of like, I don't know, 2 decades of intuition and the natural thing, given the context of today, is to build a machine learning model to do this so that we're prepared for his retirement. Yeah, I wouldn't say that, we're slowly making progress towards that end, but I think there's definitely renewed or like increasing interest in automating some of these things because we're just going to get more and more data. It's going to get more and more laborious. We always want more stations, right? And more stations means more data, means more work. Yeah.
Thank you.
Hi, Darren.
Hey.
Thanks also for the talk. I think I sort of wanted to build off the question that you just answered and the slide that you have up now to sort of either in the context of your experience at AVO or just your perspective from being one of the new, like the first, as you said, one of the people in the field at the moment. As we sort of move between the various parts, and for example, if the worker you were describing retires and there's proposal to fill that gap with machine learning, either if you've had experience with it or how you imagine it would be, what's sort of the conversation to convince people at various levels going up the chain to decision makers, so from the pickers to the people at an observatory that make the recommendation to the person who makes a decision at a governmental level, sort of to discuss either founded or unfounded concerns about how much, the question you asked, how much are you willing to give to the machine learning as far as decision making?
Yeah, I think to answer that question, AVO was considering the idea, but it's also not going to be like a snap of the finger. Yeah, he retires. Let's pull in the machine learning model and like switch everything up. I think the process is likely going to be more gradual. And I think a good case study of that, I believe this is a PNSN talk. So the Pacific Northwest Seismic Network, I think. And they gave a talk at Alaska once, someone from them. And I know they were starting to roll out and evaluating these machine learning P and S phase pickers, but at the same time, their analysts are looking at the same time periods, and they're just basically benchmarking the human performance versus the machine learning performance. And turns out there's some very obvious P and S phases to humans that are unpicked by the machine learning model, but the machine learning model also picks way more that the humans miss. So yeah, somewhere in there we're losing that great human intuition, but I wonder if at some point the efficiency of automation might just take over, accepting that as a loss, I guess.
Thanks a lot, Darren.
Yeah, thanks.
All right, we can thank the two speakers. Alberto left already, and thank them again. Really amazing talks. So if you have any other questions, feel free to contact us or just email to the speakers, and hopefully they could answer you as much as they can. So one more thing, just a reminder for our following events, which we have a master class which will take place on the 19th of August at 3 p.m. UTC. And we have another, the second session of the seminar series, which will be on the 13th of September, 5 p.m. UTC. And do check our socials to see more details of all these overall events. So I guess we can close the session. And Jeff, do you want to say something, or otherwise we just leave everybody here?
No, thanks, Ethan, for organizing, I think, a really great first event, and hope everybody can come back for the next one in a couple months, and yeah, keep your eyes out for all the ECR-Net events. And yeah, everybody have a good day, evening, night, wherever you are.
All right. Thank you so much.
All right. Goodbye. See you next time.
See you, everybody.